Hello everyone, my name is Ye. I'm the co-founder and ZK researcher at Scroll. So today I'd like to introduce zkEVM circuit optimization. So this will be more technical talk, more technical than yesterday at layer 2 beat. So the first half will be very similar because I still need some background for talking about zk rollup and EVM to, because there are so many cryptographers who are not even familiar with zk rollup. And second half will be talking about the circuit optimization and how we are writing constraints to constrain the zkEVM circuit. So basically, first introduction of Scroll, because many people even haven't heard of that. So we are building an EVM equivalent of zk rollup. So that's one sentence introduction. So then we can move to more interesting part. So the problem of blockchain layer 1 is that for each transaction, you need to broadcast that into a P2P network, and every node need to re-execute this transaction to move from state 1 to state 2. And this is problematic, right? Because this is, there is a large redundancy there because every node needs re-execution. So the idea behind zk rollup is that instead of sending out all the transactions in the P2P network, you send all the transactions in a layer 2 node. And then this layer 2 node will run some zk algorithm and generate the proof. And instead of broadcasting all the transactions, it will just broadcast the proof with some public input data needed for verification. But there are some problems because building to generate such a zero-node proof, you need to build an arithmetic circuit, right? All the zk actors here must know how hard that is to write some arithmetic circuits. And also, it needs to be application specific. For example, if your transaction is on DEX, you need to build a specific circuit for this DEX application. For example, you need to prove that your signature is correct, you have enough balance, and your path is updated correctly in the Merkle path. And so this is problematic. And worse, even you build multiple zk rollups, there is still no compatibility between two zk rollups. You still need some bridges to bridge two zk rollups. And so what zkEVM is doing is that, in a nutshell, zkEVM circuit is verifying what the Is Evm virtual machine is doing in a circuit. So instead of writing circuits for each smart contract, you write a circuit. This is more general and for verifying the execution of a Is Evm virtual machine. So basically, you need to verify that your signature is correct, the smart contract is loaded correctly, the execution trace is valid, and your storage is updated correctly. So basically, here, your smart contract is just the input of this EVM circuit. It's not, you are building some circuit specifically for some smart contract. So we have one universal circuit serving for all the smart contract logics. And before diving into even more detail, to give you a sense of what is EVM. So basically, they are smart contract developer, and they can write Solidity code, which is a high-level language for developing dApps on Ethereum. And then, there are 3 different levels. On the language level, you compile Solidity and other EVM-compatible languages down to some intermediate representation IR, which, for example, U. So this IR is still very high level, but it gives you enough information for the low-level details, and because it still remains some high-level semantics. And secondly is at the bytecode level, where it's well defined in the Ethereum yellow paper. So it basically includes push, pop, and all those stuff. And third is that you have some runtime, it's a Ethereum virtual machine, and which run your EVM bytecode opcode by opcode. So EVM is a stack-based virtual machine, and that's why another reason why it's hard to build in ZK circuit, because in ZK it's more easier to build something which is register-based. So this is EVM. And a little bit more about the comparison, there are several approaches. And on the left-hand side, Starkware and zkSync, they are building some language-compatible zkEVM. So basically, for Starkware, if you want to write some smart contract in their Starknet, you need to compile Solidity using some external compiler called warp, and then compile that down to some readable kernel, and then run on their kernel assembly code, and then finally run on their ZK virtual machine. And for zkSync, they are using the LLVM compiler infrastructure, and so they also have their circuit language called Zinc, but they are still compatible with Solidity because this LLVM IR front end, you can support the IR of Solidity and also Zinc, and then it also has its own bytecode and compile that down to zkEVM. And for what we are building, and also what Polygon Hermes is building, is that we want to build some EVM equivalent zk rollup, which means we need to interpret the bytecode of the Is Evm virtual machine. And so this zkEVM circuit, the input will be the bytecode. It's even a lower level and more compatible. So, but there are still some slightly different technical approaches to do this. For Polygon Hermes, for efficiency, they also compile this bytecode to an even smaller subset of micro opcode, and then run on their designed state machine or called UVM. And we are doing in a more straightforward way. For each opcode, we will have some sub-circuit or several gates to constrain this opcode is executing correctly. And then we will run that on our zkEVM. So, and another maybe technical difference is that from the proving system side, we are using like to write the circuit, we are using Planck optimization, and then for the recursive circuit, we are also using Planck, and we directly handle the non-native field optimization. But for polygon Hermit, I think they are using Stark to dealing with their EVM circuit, and then use Planck or Groth 16 to shrink the proof size and reduce the verification cost. So that's basically some differences. And now let's move to more technical part. And so the workflow of zkEVM is shown like in this graph. So basically, you have a sequencer and you have a prover. So this sequencer will is a fork of gas, and you can receive transactions, and then you execute transactions on your gas node, and then it will generate some execution trees. Like for example, like includes execution logs, block headers, transactions, contract bytecode, and Merkle proofs. So those will be used as witness to feed into this zkEVM circuits. So I use zkEVM circuits because it's actually composed of many different subcircuits. For example, there is a Kachak circuit for proving that Kachak hash relationship is correct, and there are a lot of other subcircuits. And those are all some components of the zkEVM circuit. So after using this witness and running some zkEVM circuit, you got multiple proofs, and each for one specific circuit. And then you got some aggregation circuit to verify that those proofs are correct, and then you generate some aggregated proof. And then you submit this proof on chain, because you want to reduce the verification cost, because you don't want to verify too many proofs, like in smart contract. And then together with some data, and you know like your transaction is valid. So now let's move to some even more technical part, like the architecture of the zkEVM circuits. So basically from the top, there is an EVM circuit, which is built for verifying the execution or a state machine, because like when EVM is executing the bytecode, it will execute opcode by opcode, right? So each opcode will be a state one state in this state machine. And so this EVM circuit is for writing constraints to constrain that this state machine moves correctly from state 1 to state 2 and state 3. So that's EVM circuit. And so you need to write some constraint to constrain the state machine. And also like for each, within one state, there is an opcode, right? So you still need to write some constraints to verify that this opcode executes correctly. So then you meet challenge 1, because there are so many ZK unfriendly opcodes. For example, there are the bitwise opcodes, which is super hard to prove in ZK circuits, because you need to decompose the value into bit and prove that every bit is 0 or 1, and then combine them together and prove that it's your value. And the second is that you have SHA-3 and all those really ZK inefficient opcodes. And so what we are doing is that instead of doing all those constraints in this EVM circuit, we will just do some lookup operations. So basically, I will just give an example. For example, if you want to prove that some value is within the range between, for example, 0 to 10. So what you do is that you generate a table. So this table, each entry is just, you iterate from 0 to 10. So it's basically, this is a table, single column. It's 0, 1, 2, 3, and till 10. And then, instead of proving that some value is within the range of 0 to 10, you just prove that this value belongs to this table. Because if you belong to that table, it's absolutely true, your range is within 0 to 10. So that's fixed table. You can, when you are doing some bitwise operations, you can just look up that you have some table which just iterate all the possible possibilities for the for example, we are doing XOR operations, you just iterate all the bits and then get the result, and you prove that this entry belongs to that table, and that's enough. And for Kachak table, it's the same. When in EVM circuit, for example, you need to prove that this input and this output has some hash relationship. And instead of writing all the constraints in EVM circuit, you just look up whether this input and this output belongs to some table. And that table is actually storing all the input and possible output for Kachak. Now just assume that this table is generated correctly, because just assume that there are some magic, you can generate this table and which has all the correct relationships between the input and output. And challenge 2 is that, as I mentioned, your Is Evm virtual machine is a stack-based virtual machine. So you need to verify that stack, memory, and storage operations are all correct. So what you do is that you have some RAM table, and for each operand, you will just look up that whether this operand belongs to that table or not. And also, I will give more detailed example later. And so that's how you do stack and memory operations. And third is that you also need to prove that the opcode you fetch is correctly fetched from your bytecode. So you need a bytecode table, and also you need some transaction table to prove your signature, and block context table to prove some other block context variables. And now, because basically what I just do is that you just assume that there are some magic and there is a table there, and you just look up everything there. But in the first place, you don't even know whether those tables are correct, right? So you need a lot of subcircuits to constrain that those tables are correct. So basically, for example, in Kachak table, you have some Kachak circuit. For proving that this input and this output has this Kachak relationship. So in this Kachak circuit, you prove that this Kachak table, all the entries in this Kachak table, input and output, has this correct mapping relationship. And for RAM table, because you involve some storage operation, so you also need some Merkle potential tree circuit. And because in Ethereum virtual machine, your MPT is actually also composed of Kachak. So you also need to look up your Kachak table and to know that this Kachak is correct. And also you have some RAM circuit for constraining that RAM table. So I will give more detailed example, it's still a high-level overview. And for bytecode table, you prove that your bytecode has some correct code hash. And there is a transaction circuit for constraining that your signature is correct, and there is a ECDSA circuit for proving that your signature is correct. And there is a block circuit. Now let's move into some more ZK and technical detail, which is especially for you guys who are already ZK experts. So to write a circuit, what we are using is that we are using some ultra-Planck or sometimes called Planck-case optimization. So basic idea is that instead of R1CS just linear combination times linear combination equal to linear combination. So, but we are using a more flexible way. We are using a table to represent your constraint system. So when you need to fill up your values or your witness, you need to fill up some. You need to put your values into some cells, and then after you fill up all the witness, this table will be full of variables. And then you can define some customized relationships. For example, there is custom gates. For example, we pick up some region, which is in the right area, and you can define the relationships for those cells within this region. I will give now a more detailed example. For example, you have some layout like that, and you have variables VA0, VB0, VC0, and all those. Those are values you filled up in this table. And then for example, you want to prove that VA5 times VB5 times VC5 minus VB6 equal to 0. So you just write that as your constraint. And what you are generating in the backend is that you generate one polynomial constraint, which is what I call custom gate. So basically, the first column, you interpret that, and you will get a polynomial for the first column. And similarly, you will get a polynomial for the second column and the third column. And so because VA5 belongs to the first column, and so you write A1x times A2x times A3x minus A2 omega x, because omega is actually your shift, because your interpretation actually happens on some FFT-friendly field, which is some Twiddle factor it's just some Twiddle factor and exponentiation of Twiddle factor. So that's how you are writing constraints. But if you are more familiar with ZK and at the end of the day, you need to linear combine all those custom gates and using one vanishing argument, it need to be divided by some x powers n minus 1 because it need to vanish on n all those rows. But so basically, these constraints can prove that all the VAI times VBI times VCI minus VBI I plus 1 is equal to 0. But what you really want is that you just want that specific area. So what you do is that you can have some selector polynomial, which is an actual column. So that this is pretty sparse, and you just open at a certain position, that area is 1. And then you multiply with this polynomial Sx. It's a selector polynomial, which is interpreted from that column. So that's, other entries are just 0, and there is just 1 there. And so because, so this equation should be hold for all, iterate from omega powers 0 to omega powers n minus 1. And because only that row, you got 0, you got 1 there, so you can only, your constraint is just constraining that specific area. So that's how you are writing custom gate. And the second thing you can use in Planck-case optimization is that you can have some very flexible lookup arguments. For example, traditional lookup arguments is proving that A0, A1, and A2 columns, all the values in those 3 columns belongs to a table like T0, T1, and T2. So that's what you have like in your traditional lookup arguments. But what we really want is that we want to look up some specific entry, right? So it's similarly, you can also have some selector there, and just multiplying with your input expression, and you just prove that this polynomial belongs to this table, and that's it. So that's basically like 2 tools we can use for writing our circuits. One is custom gate, and one is lookup arguments. Now let's look at the EVM circuit layout. So as I mentioned, like EVM circuit is for writing constraints for constraining your state machine. So basically, you have a lot of states, and for example, like we use slot to distinguish that in your position in circuit. For example, like there is slot I-1, there is slot I, there is slot I-I. Sorry, I didn't. Yeah, and like each slot will correspond to some opcode here. Like for example, like the first 2 rows are for push, and then like next several rows are for add, and those slots are for multiplication. So basically, you need to write all your constraints to constrain those opcodes like within that certain number of rows. And more specifically, there are 3 different like ranges like within one slot. So there is the context, because you need to store the context of your state machine. For example, there is a program counter, there is a stack pointer, there is a guess, and a lot of other stuff. It basically means that when you are executing your state machine, like when you reach that step, like what's your program counter, what's your stack pointer, and how much guess did you left. And secondly, the opcode and switch region. So basically, like if this region is add, then you need to open a selector at this selector add cell. So basically, we are not using too many extra selectors for constraining a certain area, but instead we are just put them all in some region, and then multiply with that number. And third is that we have some operating values, which is free allocated for some opcode specific circuits. For example, like when you are writing add, and you need 3 operands, right? You need to prove A plus B equal to C, and sometimes you need to carry. And those more opcode specific witnesses will be filled up in that region. And now let's look at a more detailed example, like how we are really writing constraints. So for example, like after you get in the execution trace, you know like what opcode you are executing and all the related witness. So firstly, you need to fill in the context of state machine, like if you are executing this state, and what's your program counter number, what's your stack pointer number, and what's your guess. And secondly is that you need to set add to be 1. Others are just 0. And then like you need to fill in the operand of add. So there is VA, VB, and VC, and carries. Because the EVM word size is 256, and we are working over the scalar field of BN254 to be compatible with Is Evm's precompile. So each cell, it works over a finite field, which is 254 bit. So like it's not enough for just putting one 256 bit. So we just decompose that into 32 8-bit numbers, and so that's why like we have a sequence of variables there. And so that's how like a more concrete deeper look into the add opcode. And so how we are writing constraints. So basically because we are not using actual selectors, we just put everything here. So we need to prove that the switch here, there is just one switch open. So for example, like we need to prove that sadd times 1 minus sadd equal to 0, because all those should be 1 or 0. And also you need to prove that there is at most 1 open. So you need to prove that everything open equal to 1. And secondly, that as I mentioned, like you need to prove for some add specific logic, right? So so as I said, like you can define relationships over certain cells. So you can just open that as add and multiply with other constraints you have. Because only if that as add is 1, you need to prove for those relationships. So those are the constraints you needed, like V0 plus VB0 minus VC0 and minus some carry. Because you are using 8 bits for each cell, so that's why you have like 256 here. And now let's move to some constraining the context of this state translation. So basically you have sadd, still sadd there, because if this slot is proving for add, and then it means when you move to the next slot, your program counter needs to plus 1. So you need to prove that if sadd is open, and then your program counter, your next program counter minus this program counter minus 1 equal to 0. And then similarly, you can also prove for stack pointer and guess. So that's for the unrolled constraints for a certain opcodes. And now let's move to a more more complicated like example, like the RAM table and how we are using circuit to constrain that a table is generated correctly. So basically, for example, like this example is used for add. For example, like your add is you need to prove that VA times VB equal to VC, right? So your first operand is VA, second operand is VB, third operand is VC. So you firstly need to prove that this VA is fetched correctly because, for example, like when you are doing add, you need to pop 2 elements from the stack and push 1 element back. So you need to prove that this popped elements is exactly, when you push in previous operations, right? So you prove that this operand belongs to some entries in this table. So there are so many columns, and you need to prove that. So I'm doing the stack operation. This is my stack pointer, and there I'm doing read or write, and what's the value. And then you need to prove that it's consistent. So this is basically how this RAM table look like. You need to prove that some operand belong to this table. And now here comes the question, like, and this is for, you pop 2 and you push 1. So every operand you need to prove this relationship holds.
3 minutes.
Oh, okay. Yes, sorry. I just need to go very quickly, sorry. So like, here's some question, like I mentioned, like, because your each cell is just 256 bits, and you can't actually fill VA here, right? So what we are doing is that instead of putting VA here, we are using some random linear combination to combine different 8 cells into 8-bit number into one encoded value A. And then like we just put the RLC encoded random linear combination combined value here, like in our RAM table. And then instead of looking up that one, you look up this linear combination. And then the problem is that your table is not constrained, so I need to write some circuits here like to constrain that your table is generated correctly. But like during the execution, you are not doing all stack operations one by one. You are actually doing stack operation, memory operation, and then maybe you again like stack operation, storage operation. So it's just math here. This is your real execution trace. But the problem is that when you need to prove for stack, you need to prove that it's consistent with previous stack operations. So you need some sorting. So when we are filling with the table, we sort the rows based on tag, address, and read-write index. And then second, we can more easily prove that the previous read-write value is equivalent to the value you are using now, because the address and the tags are just consistent. And you need to prove that the column values are valid, because for example, like there is just 3 tags and all those stuff. And you need to prove that some other related variables. And finally, that it's not just built by us. It's actually, we are using the Halo 2 optimization, so we are heavily using the Halo 2 repos. So we really appreciate that the builders who build the Halo 2 repo. And also, like, there are a bunch of members from Is Evm Foundation, especially the Applied ZKP team. And we just credit to all the community members who build this together. So this is our roadmap. We will firstly have some POC demo for zkEVM, and then testnet, and then we will have some other features like proof outsourcing and move to mainnet. And finally, last slide, like we are hiring, and check out this website. And thanks for that.
So if there's a question, we can take the question, and then you guys can eat lunch.
Okay. Which opcodes were the hardest to implement, and why? Like, for example, call.
I think there are like different groups working on different. I think like Kachak spent the most long time, because I remember like it takes months for the especially for the variable bindings. But that's a different subcircuit. But if you are talking about the specific EVM circuit, the switching logic I think is call, because you need a lot of variables related to the call context, and also like you also need to care about the revert, which I think revert and call should be the two hardest opcodes in this EVM circuit. But there are some other operations, for example, like you need to massively optimize for non-native field for ECDSA circuit to make that really small and also catch up. So there are like different challenges, like all around. But if you are just talking about the state machine translation, I think it should be call and revert.
Cool. Okay, go ahead.
As I understand, you have like really a lot of variables, and so your Blanca is a little bit modified, yeah? And what is the maximum number of constraints you have?
I think roughly we have over 1,000 customer gates. Like there are so many polynomials there. We are still doing some massive optimization for this part, and also like I think around like 100 lookup tables. That's a very rough number. Before we have done more optimization for call, because for call like it needs like just over 100 lookup tables to look up all those bytes in this RAM table. So like the conclusion is that we need like, for example, like 1,000 customer gates, 1,000 customer polynomials for writing those constraints, and it will definitely result in a lot of FFTs and multi-scalar multiplications in the backend. If that answers your question.
Yeah. Go ahead. Sure. You're eating into your own lunchtime. So.
Yeah, we can talk offline maybe.
Yeah, go ahead.
Oh, okay.
Okay.
At some point you're mentioning proof aggregation and then recursive proofs. So how are you tackling these two problems? And also, if it is with a non-native field for the recursive part, how efficient is that?
Yeah, I think I got some numbers, but I can check that offline. But I think it's maybe around like, it depends on like how many columns you are using. I think like there are two versions. One is a highly optimized version where you use slightly more columns, but it can roughly get down to I think 30K for one non-native field of optimization on elliptic curve. If you are using slightly smaller columns, then like you need over like 100K. I think like I can check with you later, like because yeah.
Perfect. So thanks for everybody for coming. And